Hello, everyone, and welcome to this edition of Science with QuEra. Today, we're going to talk about experimental demonstration of logical magic state distillation. QuEra is a very special company, and one of the things that makes it extra special are the scientists that work here. And we've got three of the top scientists to join me today. Sergio Cantu, Vice President of Quantum Systems, Zhou, research scientist at QuEra and Harvard, and John Robinson, a quantum engineer. Harry, Sergio, John, thank you so much for joining me today. So I'm going to give a quick introduction of QuEra and then hand it over to our scientist to describe this amazing paper. At any time for the audience, feel free to send us a message on the question area of the Zoom, and I'll try to incorporate them whenever possible. So just a little bit about QuEra. QuEra is based in Boston, founded on breakthrough science from Harvard and MIT. We build quantum computers based on neutral atoms. Neutral atoms went from being the dark horse of quantum computing to the workhorse of quantum computing. I think if you ran a survey today on what's the most promising quantum computing technology, I think neutral atoms would come up on top. We're not just about science, we're also about commercial excellence. Our first computer with 256 qubits is available for anyone to use on AWS since November of 22. And we recently installed a fantastic new computer in Japan. We are well-funded, recently raised $230 million, led by Google and SoftBank. So we thank our investors very much for that. And we partner with enterprises, HPC centers, and governments in helping them make the most out of their quantum innovation journey. We do it in three ways. We work with customers in three ways. One is through our quantum systems, whether on-premises or on the cloud. As we'll explain in a little bit, neutral atoms allow fantastic things that are not possible with other modalities. And when we deliver a system on premises, we also provide installation support, community development, anything you need to really make quantum a success in your area. We also do collaborative research with leading academic and commercial institutions. Sometimes it's on quantum error correction, on machine learning, on hybrid algorithms. And when we work with customers, we often do what's called application co-design. Quantum computing today is at an early stage. Computers are not as large as we would like them to be and not as powerful. So it's really important to optimize the quantum experience at all levels of the stack. So our co-design process does exactly that. It works with the customer to understand the problem, to determine if it could be solved or addressed in quantum computing today, to find the best formulation, and then optimize it to the specific capabilities of our hardware. So I invite you to reach out to us through our website or sales@quera.com if you're interested in exploring application co-design for your organization. Neutral atoms are great. I know I get paid to say that, but they really are. And let me explain why. First thing that's great about neutral atoms is that we use individual atoms as qubits. And because these are natural qubits, not manufactured qubits, they're all perfectly identical. We could put 1 million atoms together and they'll all be identical one to another. This is unlike manufactured qubits where you have to worry about yield and manufacturing variations and so on. We pack the atoms very close to each other, typically 4 or 5 microns from each other. And so you can imagine that we can, at least physically, put tens of thousands of qubits on a single machine. There are still things we have to do to get there in terms of laser power and control. But this is, again, in contrast with other technologies where you can only put hundreds of qubits on a single machine. So when you need to get to, say, 100,000 qubits, you're looking at networking an enormous amount of machines, which introduces cost and size and software difficulty and so on and so on. In our approach, not only do the number of qubits scale well, but the number of control signals also scales very well. Unlike, say, a superconducting qubit where you might need 2 or 3 control wires for every qubit, we need many, many fewer because we can shine a single laser on many qubits at once. Neutral atoms can move. we can move them, we can rearrange them at will, and that delivers what we call all-to-all connectivity. We can make any qubit interact with any other qubit, and that allows us to do more efficient algorithms, new error correction approaches. And neutral atoms can also last in their quantum state for a long lifetime as compared to the cycle time or to the operation time, which means that they certainly have the potential of running long and complex algorithms. And if you're an HPC center, high performance computing center, looking to install a neutral atom computer, you'd be delighted to find out that it runs at room temperature. You don't need the cryogenic cooling, you don't need the complexities of refills or the high energy cost or the big size that comes with alternative approaches. What you see on the right side of the screen is a picture of the computer that we recently installed in Japan. This is a 260 qubit gate-based computer, and we look forward to installing these at your organization as well. And last, just to demonstrate the point of shuttling, this is a video from a paper from work that was led by Harvard in late 2023. And it basically shows that these individual dots on the screen are individual qubits, individual atoms. And we show that we can move them at will. And when they're close, we can make them interact. So this opens the door to some of the fantastic results that you see today from our scientists. So with that, I don't know who wants to go first, Sergio or Harry or John. The stage is yours.
Okay. So yes, I'm very happy to be here to tell you about some of our work that we performed on one of these machines to demonstrate logical magic state distillation for the first time in any experimental platform. And kind of going off of what Yuval was saying, the reason we're building quantum computers here at QuEra is this underlying idea that quantum computers can solve certain problems faster than any known classical algorithm. So this is really the dream and the promise of quantum computers. And this ranges in applications from cryptography, quantum chemistry, designing new materials, and many more. So very exciting areas of development. And the one thing that threads all of these applications is a high-fidelity, programmable, and universal digital quantum computer. So that's really our goal at QuEra. And throughout this presentation, we will touch on all three of these aspects. So high fidelity, the programmability that you saw with the atom movement, and universality, which is connected to these magic states. So as you've all mentioned, we have one analog processor already on the cloud, and you can access this on AWS. This machine is an analog Hamiltonian simulator, so it's not quite digital, but you can place atoms in all kind of different spatial arrangements and do a lot of interesting simulations and optimization problems on that platform. And now we're moving on to the second generation of processor. That's this digital quantum computer that we just saw this photo of this machine installed in Japan. And stay tuned for deployment of this machine and availability. So at the core of these quantum processors are two key aspects that you've all already hinted on. So one is that we store information in the ground state manifold of rubidium-87 qubits. And so the coherence time is on the order of seconds, and atom rearrangement and gates happen on the millisecond and faster timescale. So you can implement high fidelity gates on this qubit and generate entanglement with laser beams that intersect these atoms. So that's kind of this blue shade on this photo. And you can move atoms around. So you can entangle certain pairs of atoms and then mid-circuit rearrange them in a coherent fashion. So we can generate this all-to-all connectivity that is very powerful when designing new algorithms and was really key in this demonstration of magic state distillation. So here's another video, and we'll show yet another one from the Gemini machine, but this is a video from the Harvard experiment where they kind of rearrange the atoms and perform these 2-qubit gates to generate interesting connectivity for quantum simulations. So on the Gemini machine, one important piece is high-fidelity gates. At the core of every digital quantum computer, you need to operate the single qubit gates and 2-qubit gates with high fidelity. And we've demonstrated on our machine global single qubit gates beyond 99.9%, approaching 4 nines of fidelity. And that's across the full array. So for us, that's the full 200 micron field of view. And sometimes in algorithms, you want to implement local single qubit gates. So not across the whole array, but a certain subset of atoms. And for that, we show 99.917% gate fidelity. 2-qubit gates are very important and turn out to be kind of the most crucial gate in most algorithms. And for us, we perform parallel 2-qubit gates across up to 65 pairs of qubits. So this is an image of atoms spaced close together and in this 5-row arrangement. And there we get something around 99.5% gate fidelity, which is on par with the state-of-the-art from other labs with single atom or neutral atom qubits. And you can also see work from Harvard and others in this direction. And one crucial ingredient to this whole story is really magic states. So when we talk about all of those applications, you'll often hear, oh, we need millions or billions of T states or these magic states. And what are these about? And why are they so important? And it's important because we want to get a universal gate set. So we perform quantum error correction to correct errors that occur during circuits. But we also need to generate a universal gate set so that we can implement a general quantum algorithm. But the Easton no-go theorem tells us for a given quantum error correcting code, you cannot have a universal transversal gate set. And so what that means is I can't do a complete gate set transversally, which means taking logical qubits and performing, say, 2-qubit gates by simply overlapping 2 logical qubits together. And this is a really big problem in generating a universal quantum computer because you can't implement these magic states with quantum error correction. So we need some other strategy to do this in a fault-tolerant way. And the one general approach, although there are some other approaches, is to use transversal gates for most of the operations. So for simple Clifford rotations, like pi/2 pulses. And then you need to prepare these magic resource states to help implement the, for example, the T gate. And so a crucial question is, how are we going to prepare these high-quality magic states and implement them in a circuit where here the T gate is applied to the qubit on the bottom side through gate teleportation. So we need to somehow produce these high-quality T states with very high fidelity. And you want to encode those magic states, crucially, in logical qubits so that they are protected. And before our work, there was a lot of other work in encoding magic states into logical qubits, performing in the middle some flag-based approaches to improve the fidelity on trapped ion systems, and some nice work from Quantinuum as well, implementing logical T-gate. But one thing that's missing here is going the full distance of distillation and implementing logical magic states. And one crucial part is growing the codes. So having larger and larger logical qubits make them more and more protected. And whatever method you pick for producing these high fidelity magic states needs to be kind of scalable so that we can see into the future into very low error rates. So the general idea how are we going to produce these high-fidelity magic states is a concept called magic state distillation. And the schematic here shows on a high level how this works. You first produce lower fidelity magic states, some number of them that are input into the algorithm. And by performing distillation, you go from, say, 5 high quality or lower fidelity magic states to 1 higher fidelity magic state at the end. And so you use these noisy magic states. You can perform actually multiple rounds of distillation. So you can imagine running 1 round, you improve the fidelity, and then you can just kind of recursively run this kind of algorithm. And the key idea is that you first protect these qubits in what we call a data code. So that's the quantum error correcting code that we encode the magic state into. And then the so-called distillation code actually performs the distillation. The idea is that the output magic state should suppress any input error quadratically, or potentially to even higher order, depending on the distillation circuit. So before our experiment, there were existing experiments on performing physical magic state distillation. So we like to give credit to the work before. On the left, there's 2 examples of performing physical magic state. The problem is these physical qubits aren't really protected. So if you look at this circuit, there's a lot of C0 gates. There's a lot of errors that accumulate during the circuit. And so it doesn't really work with physical qubits because you need to protect your qubits from all of these operations. And so it turns out there's a lot of challenges in implementing magic state distillation. You need to somehow encode MIDI logical qubits in parallel into magic states. You need to now perform a lot of transversal gates between these logical qubits. And often schemes require conditional logic. So you need to make measurements and perform operations based on those measurements. And so there's a big challenge of how can we operate logical magic state distillation with today's systems. And I will hand it off to my colleague Sergio, who explains exactly how we did this in our system and how we leverage all of those very nice benefits that Yuval is commenting on what neutral atoms give us as a platform. And so I'm not sure if there's any questions at this stage, or we can.
Thank you, John. And yes, my name is Sergio Cantu. I'm Vice President of Quantum Systems. And thank you for Joel and John for the overview and the relevancy of magic states and the overall state of producing magic states. So now I'll go over what has been the recipe that we've been implementing on our Gemini QPU. So if you look at the overview of our paper, we break down the distillation of magic states the following way. So first, we had physical qubits. And as John said before, there's been challenges on distilling at the physical layer. So for that, we decided to then encode the physical qubits into logical qubits. That way we can better protect those physical qubits once they go into the logical qubit against errors. And then once we have those logical qubits, we can start now doing the process of now how good can we encode a particular physical qubit state into these logical qubits. Once we generate multiple copies of the magic state, then we can now run distillation code, as John mentioned earlier. And then by looking at now the output of this distillation code, we can then look at what the qubits that come out now can act as ancillas that can flag whether this distillation was successful. And we'll go into each one of those as to what step corresponds to going from the first layer of how good are physical qubits, what is the level of encoding that we have, how do we optimize the circuit, what was our overall performance on encoding a particular state, what is the overall performance of the distillation of the circuit, and what has been overall approach for decoding what the output of this factory has been. and then we'll go over questions at the end. So let's go to the first part. For the encoding circuit, this is work that Sunny and Casey from MIT and Casey here at QuEra, led by Harry, have been pioneering. And this is basically taking on a particular physical qubit and then mapping it up into a logical qubit. The platform of neutral atoms allows you to really be flexible. And in the same QPU, we were able to scale and try different distances for this particular color code. So in this case, we use color codes for distance 3 and distance 5, as shown in this circuit schematic. And then this was done by trying to optimize the number of resources, the number of qubits that are necessary, as well as the number of gates that are necessary to encode. And for distance 3, there was some work on optimizing the particular encoding circuit, as well as for distance 5. So this is a very active area of research in which not just make sure that we can do experimental progress, but also optimizing the circuits for encoding as well. So now that we chose the particular encoding circuit that we want to do, then let's look at what's been our performance in encoding these qubits. So yeah, and it's important to point out that as you will show in the video, since we also shuttle atoms back and forth, the circuits are optimized. The location of the gates are also optimized for atom movement. Cool. Like our citation earlier pointed out, for Continuum's paper, there was this particular good distillation circuit, but you can see that there were about 17 qubit gates that needed to be implemented. And this is, I think, where being online has been, fruitful for us. We saw that Craig Gigny actually published an update on the circuit in which, you can see that the overall number of 2-qubit gates has been reduced. So in the particular circuit that Craig Gigny posted, there are basically 6 CC gates. And this is where I think is a comment that we got from our paper when we posted it on the archive, which is that, just gave us confidence that we're going the right track. So I think this is also the first citation of a tweet that I've seen on a Nature paper. But basically, what we did is took the circuit that Craig posted, and we were able to optimize it now to basically 3 layers once you account for local rotations and overall movement. So now this is the final distillation circuit that we implemented in our QPU. And you can see that basically we start now with 5 logical qubits. And after the particular circuit that we designed, then at the output, 4 of those qubits act as our ancillas that we can use to basically extract the distillation syndromes, and then from there confirm what the output of this factory is. And this is putting it all together. We see the distance 5. So every row in this particular video corresponds to a different logical qubit. We have 17 qubits per logical qubit. And basically see how this is the encoding layer in which we take all the physical qubits to produce all the logical qubits in parallel. You see basically all the movements that happen, and then as the encoding ends, you see that the logical qubits now start acting, and the factory starts kicking in. You see that now the logical qubits are acting in parallel overall through the whole circuit compilation. And it is important to point out that this layout really was optimized for parallelism of control, taking account movement, local rotations, and we used the exact same geometry to run the distance 3 distillation. So we were able to produce 2 factories in parallel by just basically working with less qubits and parallelizing still the control across these 2 factories. Okay, so with that, let's now go through each step and let's look at the overall experimental results. I would like to highlight that this, of course, has been a very big company-wide effort for this particular experiment. It was led mostly by the Gemini processor team, Tato Sales, John Robinson, Nikki, and myself on the experiment side, and very heavily supported by the QEC team led by Harry and other people at QuEra. So, okay, so now let's look at the distance 3, just for keeping things simple. we'll take a physical qubit, we'll rotate this physical qubit in the XY plane, and then we'll pass it through our encoding circuit, and then through the stabilizers measure what is the overall logical qubit that we get. And what we see is basically that by looking at the error-corrected values, the overall fidelity that we get, as well as once you do, you can condition with perfect stabilizers this particular logical qubit, and we see that the fidelity of the qubit grows, which is basically saying that going through this encoding circuit allows you to now have, even though you pay the price that the gates that you apply to encode make you overall qubit quality degrade, the fact that you have now stabilizers and you can measure the logical qubit allows you to be able to correct these errors. So, and we see that now by injecting a particular magic state across 10 logical qubits, we can verify that the raw fidelity is about 94%. But by looking at the stabilizers, we can correct, and if we work on perfect stabilizers, then we can get back to 98%, a little bit more than 98% fidelity, and this is pretty consistent across all 10 logical qubits. Cool. So for the next slides, I would like to point out that we'll be working with the error-corrected value of 95.2% fidelity, and then we will be using this to compare against what is the output of the distillation. So we just took our physical qubits, we encoded them up into a logical level, and now with these logical qubits, we'll run them through our logical distillation, and we'll see what is the output and what is our logical and stabilizer outputs. So it's important for me to point out that again, like I said, the 4 qubits that are not the distillation output can be used for ancillas, and this ancillas allows us to determine whether the distillation was a success or not. Cool. So then from here, I would like to comment on what is the overall performance that we do. How do we decode the overall syndromes that we can extract, and how can we use this to improve the criteria for success for this factory? So for this particular experiment, we use correlated decoding, which the idea is pretty simple. So for a particular physical error that happens somewhere across the particular circuit, in this case, the distillation circuit, any physical error propagates through the qubit gate as a correlator error across logical qubits. So that means that by looking at the distillation syndromes and looking how these errors correlate, we can backtrack and understand where the error most likely happened, and then use this information to correct the syndrome extraction. So so in a separate work, the QEC team has shown, and as well as Harvard, that fault tolerance of the algorithm can substantially reduce the time cost for QEC, and this is not really a bottleneck for scaling the algorithms going forward. And there's a lot of ideas going on right now for how to improve the overall algorithm for decoding, and this is a very active area of research. And I'll highlight some work that Harry and NVIDIA have also been working on. Great. So just to finalize, the particular decoders that we use in the experiment were the maximum likelihood encoder, but in separate work, Harry and the NVIDIA team have also been looking at how to use machine learning to overall improve the results of the distillation factory, and at the same time to improve the overall time for decoding. And we want to get to the point in which decoders can be used in real time, so that we can improve the overall execution of quantum circuits. So this is a very active area of research, and here I'm highlighting the QR code for people to follow the link and learn more of this work. Yeah. Great. So looking at the output of the magic state distillation, what we see is basically by looking at the outputs of the distillation, for this particular 5-to-1 qubit code, the acceptance rate is about 1 in 6 with no errors. So this is basically what we look at our maximum for total accepted fraction. But what we see is by basically conditioning on the outputs of those stabilizers, we can basically compare against what is our error-corrected injected fidelity. And what we see is that by basically using the ancillas that we have from the circuit and using this to even condition it on more perfect outcomes, as we start basically reducing the acceptance criteria so that we have better and better outputs, we see that the overall fidelity of the magic state increases. And all the way to basically once we condition on perfect stabilizers and there's logical qubits, we get about 99.4% fidelity. So we see a continuous trade-off between these logical qubits depending on the fraction that we decide to accept. And this is publicly data that is available now on Zenodo for people to look into. But what we see is that basically for both distance 3 and distance 5, by flagging and improving the overall condition of acceptance criteria, we see that the fidelity improves for both distances. So, but this is not all. We would like to check how much is this particular experiment resistant against errors. So, conditioning on perfect stabilizers, we basically add coherent errors across the logical qubits that we have, and then we see how good is the factory protecting against this particular errors that we input. We see is that as we add errors into these logical qubits, we do see quadratic suppression of the errors that the factory has. So that's fantastic because it means that the overall factory is working as intended, and we see improvement across both distances. So cool. Putting this whole story together, what we see is that basically the price that you pay for going up larger distances can be compensated by the fact that now you have at larger distances better idea of where the errors are coming from, so you can quantum error correct. Now we see is that after running the particular logical qubits through the factory, still the magic state factory fidelity is still pretty high. So of course this comes at the price of the total accepted fraction, and of course this would all be benefited by having even higher gate fidelities. But to me, this feels like a great, shown of improvement of how can we use logical qubits to now really use and correct for errors across the different circuits that we want to implement. So with that, this is a very active area of research, and this is just an example of the logical qubits that we have available to us. And stay tuned for the next iterations of the circuit.
Thank you very much, Sergio. I do have a couple of questions, and of course, if someone from the audience wants to add, you mentioned optimizing for atom location and moves. And for some people listening to this webinar, this may be a foreign concept. So could you explain why that's necessary?
Yes. So, for the qubits that we have, the particular coherence that we have across the machine and overall, reducing the time that it takes for different operations that we want to do, placing the atoms in the right locations, as well as choosing how you want to move them to maximize parallelism is a strategy that we typically have for making sure that the qubits stay at high fidelity. Right? So it's not just placing them close, but also how can we place the qubits such that we can move them in parallel or apply gates in parallel so that we can reduce the overall time for execution.
The second thing is even going back to the beginning. I understand that magic states are important because if you just have Clifford gates, you can only reach certain points on the block sphere, and with these magic states, you can essentially reach any point. Is that correct?
So the idea is that having the magic state allows you to have further rotations, right? So that you can go from basically along the 1-1-1 axis, you can rotate. So it's not that, this particular state gives you arbitrary rotation, but in combination with the rest of the gates, you can have now more flexibility.
And people sometimes use magic or T states and T gates interchangeably. Why is that the case?
That is because through basically applications like teleportation or how we can map a particular state into another, it looks very similar as if you apply a gate itself. Right? So a gate, when we think of gates, we typically think of and for us, it's shining some laser light somewhere or applying some perturbation to the atom. But you can also, in the similar way, have a state that is prepared beforehand and through basically conditional operations like C0 or ZZ, you can basically map information back into the qubits that you have. So that's why it looks similar, whether you call it a T gate or a T state.
So if you have a T state and through a teleportation circuit, you can actually implement a T gate.
I think that's exactly like, say you have some logical qubit, and at some point in your algorithm, it's asking you to perform a T gate. So for whatever reason, you need to rotate by pi/4 on the equator. In order to do that, you need to prepare a separate T state to then kind of do this teleportation thing. Kind of sounds like a different kind of magic, but to teleport that into this other qubit. So that's why they're kind of interchangeable in at least on a high level, because in order to produce a T gate, you need a T state in this quantum error correction framework. And if Harry could probably potentially phrase it even better, but yeah.
Why is it called magic? Why is a magic state called magic?
Oh, that's a good question. Like a historical reason.
I always interpret it as basically, when you pay the price of encoding and you lose this access to that you don't have a full set of transversal operations, the fact that you can make the state separately and then apply them through teleportation, to me, it feels almost like it's a magic state that allows you to bring back the universality. But I don't know, maybe Harry knows more of the historical context of what they're called magic.
Yeah, I think it's kind of exactly what you said, where it's the thing that gives the power for you to do non-classical stuff. And so people were creative in their naming and called it magic. Yeah.
Yeah. I guess another name for magic states is also like, resource states, right? Like, it's a state that allows you to have resources to bring back the universality into the circuit.
And in a real life circuit that does something truly useful, would you have multiple sort of magic state factories along the real circuit?
I mean, I don't know if you have multiple, but you have a factory always producing magic states. So magic states will be continuously being added into a useful circuit.
How good can the distillation become? I mean, can you take more logical qubits? Can you do this multiple times? Or how good does it need to be?
We didn't show this in the paper, but like John mentioned earlier, nothing stops you from making multiple magic states and kind of bring them back and run them through the factory again. But something that I would also like to point out is that we also showed that having the different distance across, right, protects you for errors. So you have now two axes for working, right? The one is that you can have multiple rounds of the same factory, but also you can grow the distance, and that gives you scalability on both axes.
Now, this process of magic state distillation, sometimes we refer to it as taking, crude oil and refining it into jet fuel. And I know that you and the team have worked on this paper for a long time. Take us behind the scenes. What was the most difficult or challenging portion of getting to this amazing result?
I would say getting the injected or the encoded fidelity high enough to begin with, right? So to run something like magic state distillation, there is a threshold. It's not as stringent as the typical quantum error correcting threshold you hear about with surface codes, which is about 1%. But for us, because distillation itself also introduces errors, like we really needed to make the whole circuit execute in high fidelity. So I think in a big picture, right, you have the quantum computer, you have all of the gates working as their own individual units, but putting it all together with the proper circuit design, like that is a few magic, again, not to overuse the word magic, but having the right people from the experimental side and also from the theory side, like Harry, Casey, and others, kind of on the compiler, like when we're talking about atom placement, getting the whole thing to work all at the same time took quite a lot of time, and it kind of forced us to learn more about the quantum computer and then how are the ways, you need to tune it up and make it work, hopefully for even more circuits. But it's a bit of a cop-out experimental answer. It's like trying to make it work is the hardest part.
I mean, there were days that we were like even discussing like, should the atoms move left or should they move right?
Yeah. And you try all different, you're trying just all different things in your toolbox to get the highest performance. Yeah.
And just connecting to the beginning of the talk where I was describing some of the features of neutral atom computers, which of these features make it easier to do logical magic state distillation on neutral atom computers?
All right. I think the unique thing about neutral atoms, okay, and some other modalities have similar flexibility, but being able to perform these transversal gates. So in that movie, you saw us pick up logical qubits, even 2 at a time, and move them in parallel. That ability means we can have this connectivity between the logical qubits that another, say, superconducting qubits, they would have to perform perhaps more gates to get that connectivity. But I would say it's a blessing and a curse. Like the fact that you can move the atoms around in this parallel way is very powerful. But you also need to do that correctly in a low noise way, right? So it's somewhat easier said than done, but without that, implementing this circuit would get very challenging and potentially impossible because of the accumulation of all of the errors.
Very good. So I think we're at time. This was great. Thank you very much, Sergio and John and Harry. Join us in the near future for additional science with QuEra webinars on some exciting research done by QuEra scientists in collaboration with Harvard and MIT and other collaborators. And visit us on QuEra.com to learn more about our fantastic neutral atom computers and see how we can help you in your quantum journey. Thank you very much, everyone.